Some say that the quickest way to a point is a straight line, but is that actually true? What if, instead of traveling along the surface of the Earth, we dug a hole and made a tunnel to the point and let gravity take us there? Would that get us there any faster? Let's find out. First, we must look at connecting 2 points on the surface of a sphere as shown here. As we travel along the line, the force of gravity acting on us would change out to how far away we are from the Earth's center, as the only mass contributing to the force is the mass of what's between us and the center. So, substituting in the mass with respect to our position, and here we also make the assumption that Earth has a uniform density. We can now use Newton's second law, F equals ma, and plug in our equation for the force. Here we see our force is equal to our mass times acceleration. This equation turns out in the form of a simple harmonic oscillator with respective k and m effectives. Solving this simple differential equation, we see that r of t is equal to the radius of the Earth times cosine of square root of the gravitational constant times the mass of the Earth over the radius of the Earth cubed times t. Solving for the period, we know that omega is equal to square root k over m. We see that our time for a full oscillation in a straight line tunnel is equal to approximately 84 minutes, which is about 42 minutes to get from one side to the other. It's also interesting to note that the period of the straight line solution does not depend on any starting conditions, so 42 minutes will be the time traveled no matter where you are traveling to. But is there an even faster way? For this instance, we will look at a Brachistochrone curve for a mass moving through a sphere. A Brachistochrone is a curve of least time traveling under the force of gravity. Solving this problem, we will look at the system's energy. In this case, we start with no kinetic energy, so let's look at potential first. The potential energy is defined by the integral of the force from the point of the center to the surface. After finding potential energy, we can find the total energy of the system. As stated earlier, there is no kinetic energy at the surface. So now we have an equation for total energy and we can solve for our velocity. With making the simplification that g is defined as the gravitational constant times the mass of the Earth over the radius squared. As we are looking for the quickest time, we will come back to our time equation, which is defined as the distance traveled along the path divided by the velocity integrated from point A to point B. Plugging in our respective equations, we can find the Euler-Lagrange equations in this form, as they do not depend on time. After going through the integration, we find two coupled differential equations. Combining these two equations and solving, we find our equations of motion shown. These parametric equations represent those of a hypocycloid. A hypocycloid can be defined as a point on a circle that is rotated around the inside of a larger circle. The parametric equations for this point are shown. The path this point makes is dependent on the ratio of a over b, a being the radius of the large circle and b being the radius of the inner circle. As we increase the ratio of a to b, the amount of cycles the inner circle goes through increases. Using the parametric equations we found for the spherical Brachistochrone, we can look at a simulation of a tunnel through the Earth. We see that it has a path of that of a hypocycloid, and if we go through the solution for time, we see that t is dependent on s, the distance between points on the surface. In this simulation, we find that we have a time of approximately 27 minutes. That's 15 minutes faster than that of the straight line tunnel. This idea of a gravity train and the benefits it could have on travel has been around for quite some time. It has even appeared in some movies and video games such as the remake of Total Recall and Super Mario Galaxy. But why are there none in existence today? There are quite a few reasons as to why we have yet to see anything like this. First and foremost, these potential tunnels would pierce the Earth's mantle, in which there are no known materials that could handle this extensive heat. Secondly, the tectonic plates in the Earth are always shifting, leading to potential tunnel collapses. Another factor to consider is that of money. The cost of a transportation system like this would be immense. It may just be better off flying.